My name is Matt Yedlin. I'm an associate professor in the Department of Electrical and Computer Engineering and a faculty in residence at UBC Studios and EML. I initiated the project, the ECG Visualization Project, to improve cardiac diagnostics in the long term. It is really important for the cardiologist to see a large set of data at once and make diagnostic analysis. But to do that, they would have to look at a very long, one-dimensional series of peaks. And we decided to improve that by creating two-dimensional images that could be scanned and looked at for periods of hours of recording. And then with those two-dimensional images, we wanted to create analytic diagnostics using machine learning by analyzing the strips in the messages that we receive in the two-dimensional images and their correlations.
Hello everyone, my name is George and I will walk you through the ECG visualization classification project. So right off the beginning, we're going to discuss the initial idea and how we came up with it. Here is a typical ECG diagram. It is essentially a 1D signal which measures the voltage on the heart as a function of time. Typically, a cardiologist requires 30 minutes to 8 hours of ECG data for medical diagnostic purpose. The traditional ECG is built in a 1D format, which can only display 1 minute of ECG on one screen. So we came up with the idea of developing a data-driven ECG diagnostic tool using machine learning for cardiologists. Here is the approach we're using. First, we convert the 1D ECG data to a 2D image format by displaying the same number of heartbeats in each row. And then we process the image to eliminate the noise and get the image data into the correct color space and scale it to the proper size for the AI model to work on. Now we are looking at a new way to visualize the ECG data in the image format. It plots the 5 minutes of ECG data in grid levels. The image has 20 rows in total and each row contains 15 seconds of ECG data. The data is displayed in strips so it can be fit on one screen. I highlight the red circles on the image here. They indicate the peak of the heartbeat. One cycle is the distance between two peaks. Therefore, a large separation between peaks of the ECG is the lower heart rate that takes more time. A short cycle has less white space between the peaks. That means we can use this figure for the diagnosis of heartbeats. We have about 30 peaks per row, so that's 700 cycles in 5 minutes of data. About 25 minutes recorded ECG data is visualizable on one page. Compared with the traditional one-dimensional display that will take 180 screens, we're able to see the heart rate behavior on a large time scale. We can't do that in the normal display. Here is a more clear visualization for correcting the edge effects in the data. The alignment is much clearer to note any change in the heartbeat. Given the ECG data, we want to do a classification to separate them into two classes. One is under the treatment while the other one is not. We apply the principal component analysis on the datasets. PCA is an unsupervised learning technique for reducing the dimensions of the datasets. Here is the key approach we are using. We compute the covariance matrix of the ECG datasets, pick the top two eigenvalues, and project the dataset into the 2D plot using the eigenfaces. It did not result in data separation into two classes. More future work will be done to achieve that. This summer, we are using Amazon Web Services for machine learning training. AWS is a cloud computing platform that provides users with compute storage as needed. Compared with the traditional computer, AWS offers much stronger computer power and database storage. We're using AWS SageMaker for machine learning coding and training, and use S3 bucket to store the ECG datasets. And now I will pass it to Janelle talking about the game model.
Since this project will be used for medical purpose, it is essential that AI we are using is highly accurate. For this purpose, we need thousands of datasets, but we only have 31 datasets. To address this challenge, we make use of another AI network called GAN. GAN stands for Generative Adversarial Network. Created by Ian Goodfellow and his colleagues in 2014, this machine learning framework is capable of creating thousands of datasets from few existing real-world data by using two neural networks called the generator and the discriminator. The generator gets seed or noise as an input, which specifies the initial state, and its function is to generate data set that resembles real-world data using this seed. The discriminator, which is trained using real-world data, gets generated image as an input, and its task is to distinguish between real-world data and generated data. If the discriminator labels image as generated image, feedback is sent to the generator, and it now must learn and include more patterns in the generated data so that it resembles real-world data. This process continues until the generator generates images that are labeled as real image more than half of the time by the discriminator. I'll pass on to the George so that he can talk on future work on this project.
In terms of the future work, instead of using random noise for the GAN model, I'm planning to apply Fourier transform to the ECG images for GAN training and compare the advantages in the quality of generated data. The generated dataset will be used in deep learning classification neural network algorithm. And also I will apply PCA to the entire ECG datasets and find the time window to separate the data into two classes. And that's the machine learning part we worked on this summer. Here is what it looks like in Unity 3D, next to a more famous example of time series analysis. Thank you.